The Coma cluster is one of the richest clusters that we have in the local universe. The Coma cluster is about 300 million light years away. It has many, many galaxies, thousands of galaxies packed in a dense region. If you have galaxies that are densely packed in a certain region, you have physical processes that act on the galaxies that would be very different from the physical processes that would act on the galaxies in less dense environment. And those processes can radically transform galaxies. Shardha Jogee, Associate Professor at UT Austin. Over the past 3 or 4 years or so, my student, Team Manirina, and I have been doing a survey of the Coma cluster of galaxies using the Hubble. And this is being done in collaboration with a large international team of astronomers. We are using the advanced camera for surveys to get the observations, and the advantage of that is that we can get really high resolution, sharp images of the galaxy, so we can really dissect the structures. And the Hubble data also allows us to get information on the different kind of stars that exist in the galaxy. And in addition to the Hubble, we are also putting data together from other instruments, ground-based telescopes, as well as the infrared Spitzer telescope, the Galaxy telescope that does ultraviolet observations, and also XMM Newton, which is an X-ray telescope that tells us about radiation at X-ray wavelength, very energetic wavelength. And these data put together can tell us about the whole history of galaxies, the black holes that are forming, as well as more recent obscured region of star formation that we can then combine with the Hubble data to get a clearer picture.
My name is Irina Marinova, and I am a fifth-year grad student at the University of Texas Astronomy Department. Hubble provides a significant advantage over ground-based data because of the resolution that we can achieve. The resolution is many factors greater, and we can see structures in these galaxies that were completely washed out in previous observations. And so it lets us study the structure of these galaxies in a lot more detail. And also it lets us see much smaller, fainter galaxies that people couldn't see with ground-based observations in the past. And these galaxies are very interesting because they can tell us about the formation of the cluster itself. A metaphor that's often used is that of a big city, like a densely populated city like New York. So the Coma cluster is the densest cluster environment that we know of in the local universe. And so if you think of it like New York City compared to a rural environment, it's interesting to study because we can look at how galaxies evolve differently when they're packed in a dense environment and compare to galaxies that we see that are a lot more isolated.
The kind of galaxies that are very common in the field are Milky Way type galaxies, spiral galaxies that have a lot of gas, they are forming stars, they have prominent spiral arms. But if you look at a cluster, you see a radically different population. You see hardly any galaxies that look like the Milky Way. You see mostly galaxies that are very red and dead, so they have no gas, they look featureless, they're basically not doing anything much in the present time. They also are very different in shape from the field galaxies. Spiral galaxies tend to be disky, like a frisbee. Galaxies in the Coma cluster tend to be what we call bulge-dominated, so they are rounder, more like a watermelon. And so the shapes, the colors, the appearance of the galaxies that you see in cluster environment is very, very different from what you see in the field. And astronomers have for a long time tried to understand why that is so. And studying a cluster like Coma will by itself probably not answer the full question, but it will give us a little bit more insight into what happens.
In my project, I want to look at disk galaxies specifically, and I want to compare their structures in a dense cluster environment like Coma to how their internal structures look in isolated galaxies. And in particular, the type of structure that I'm looking at is something called a stellar bar, which basically looks like a big straight line in the middle of the galaxy. In the field, we know that about 60% of galaxies have these structures, and they're important because they can redistribute gas on the inside of a galaxy, and it can trigger large bursts of star formation in the middles of galaxies. And so these bar structures can drive the evolution of a galaxy from the inside out. We want to see whether the amount of galaxies that have these types of structures is different in dense environments than it is in isolated galaxies.
My name is Tim Weinzierl. I'm a fourth-year graduate student at the Astronomy Department at the University of Texas at Austin. The Coma cluster, it's so rich in the different kinds of galaxies that it has. It's a very good laboratory for studying galaxy formation, and the main reason is because you have different morphologies in the very center and toward the outskirts. And so what I'm going to be doing is looking at spiral galaxies both in the center and at the outskirts. We can learn something about how these disk galaxies form, and also about the processes that influence the evolution of the disk galaxies over time. One idea is that they form through mergers of other gas-rich spiral galaxies, and these mergers can create a large spheroidal bulge, basically an elliptical galaxy, and over time a disk can grow around that bulge and make a spiral galaxy with an elliptical galaxy living in the center. Another idea is that the bulges in these spiral galaxies form through secular evolution, slow disk processes that over time gradually build up a bulge in the center. And the reason we're looking at the Coma cluster is, well, there could be differences in how galaxies form based on their environment. Now, the galaxies inside Coma are not merging now, but they may have in the past, and so it'll be interesting to make a full comparison between the field and cluster. It's very cool indeed. It's not unheard of for graduate students to be working with Hubble data, although it is relatively hard to get Hubble data. It's very, very competitive and very oversubscribed. In the latest proposal that was submitted, there were 60 co-investigators listed on the proposal. That's quite large in astronomy, and these people are all over the world.
I think this kind of collaboration is also more and more the way astronomy is going these days. There are more large surveys, there are more this kind of large team coming together, bringing many different data sets together, and that allows you to attack questions that you could not do on your own. A deeper question, larger question. I think it's a good experience for graduate students. You get to see science, I think, put in a larger context. I think another advantage of working in a big team like this is you are aware not just what you are doing with this data set, but you're aware of what 10, 12 other little groups are doing, addressing 10, 12 other different questions. So I think also the breadth of knowledge and your awareness of the kind of science that can be done gets increased simply by being there.